In this video, we will discuss principle of mathematical induction. In mathematics, there are certain results or statements that are formulated in terms of n, where n is a positive integer. To prove such statements, principle of mathematical induction based on a specific technique is used. Here, induction means we use the generalization from particular cases or facts. Hello friends, you are watching YouTube channel Number Collage. This channel features easy to understand concept videos on mathematics. The proof by principle of mathematical induction completes in 4 steps. Step 1, foundation. Step 2, assumption. Step 3, succession. And step 4, induction. In order to understand principle of mathematical induction, we will make use of domino effect. Suppose a set of thin rectangular tiles, as shown in the figure, are placed on one end. When the first tile is pushed in the indicated direction, all the tiles will fall successively. This is what we know is domino effect. Now here, to be absolutely sure that all the tiles will fall, it is sufficient to know that number 1, the first tile falls, and number 2, in the event that any tile falls, its successor necessarily falls. We will try to understand this through the 4 steps that we have mentioned earlier. In step 1, known as foundation, the first tile falls down, followed by it, second also falls down, then third and fourth, and so on. In step 2, known as assumption, we assume that kth tile falls down. In step 3, known as succession, when kth tile falls down, k plus 1th tile will also fall down. In the last step 4, known as induction, we generalize from these particular cases or facts that it is true that all the tiles will fall down. Now we will see how to use these 4 steps to prove a mathematical statement. We will write 1 as 1 square equals 1, which is the first odd number. Then 4 equals 2 square, which we can write first odd number 1 plus second odd number 3. 9. 3 square equals first odd number 1 plus second odd number 3 plus third odd number 5. 16 equals 4 square, which is first odd number plus second odd number plus third odd number plus fourth odd number, etc. So we see a pattern here which we can write as 1 plus 3 plus 5 plus 7 plus so and so forth. Nth term of the odd number will be 2n minus 1, and that will be square of n, which are nothing but these squares of successive natural numbers. Here we get a statement that sum of first n odd natural numbers is the square of n. So we write the rule or the foundation statement as Pn equals 1 plus 3 plus 5 plus 7 plus so and so forth plus 2n minus 1 whole square equals n square. Now we wish to prove the statement Pn is true for all n. Now the step 1 is to prove P of 1 is true. P1 is 1 square, which is 1, is true. In step 2, which is the assumption step, we assume that Pk is true for some positive integer k. In step 3, we need to prove that if Pk is true, then Pk plus 1 is also true. Now since Pk is true, we have 1 plus 3 plus 5 plus so and so forth plus 2k minus 1 equals k square. Now we will consider by putting k plus 1 in place of this k. We write 1 plus 3 plus 5 plus so and so forth plus 2k minus 1, which is up to pk now. Now we will substitute k plus 1 in place of this k and write 2 times k plus 1 minus 1 equals, now up to this we can write this k square, to which we will add this, which is 2k plus 1, and this is nothing but expansion of k plus 1 whole square, which implies pk plus 1 is also true, which is the last inductive step. Hence, we conclude Pn is true for all n. In the first example, we will prove 2 plus 4 plus 6 plus so on and so forth 2n equals n into n plus 1. Here Pn is 2 plus 4 plus 6 plus so on and so forth 2n equals n into n plus 1. We will prove that P1 is true. So here P1 will be 2 into 1 equals 2, which equals 1 into 1 plus 1, that is 2. So that implies P1 is true. Next we assume Pk is true for some k, a positive integer. So we write Pk as 2 plus 4 plus 6 plus so on and so forth to k equals k into k plus 1 is true. We name this 1. Next, we will prove that pk plus 1 is true. So, pk plus 1 will be, we write pk up to this. So, 2 plus 4 plus 6 plus so on and so forth plus 2 times k plus 1, which equals putting k plus 1 here and putting k plus 1 here again plus 1 gives us k plus 1 into k plus 2, which implies pk plus 1 is true. So from the principle of mathematical induction, we conclude that Pn is true for all natural numbers n. We have to prove by method of induction 1 into 3 plus 2 into 5 plus 3 into 7 plus so on and so forth plus n into 2n plus 1 equals n by 6 into n plus 1 into 4n plus 5 for all natural numbers n. First, we will assume the statement to be proved as Pn, which is this whole thing. In step 1, we will prove that P1 is true. So, LHS is this n into 2n plus 1. By putting n equals 1, we get 1 into 2 into 1, that is 2 plus 1, that is 3, which will be 3. Now in RHS, here we will put n equals 1, so that will be 1 by 6 into 1 plus 1 will be 2 into 4 into 1 will be 4 plus 5, that will be 9. So it will be 2 ones are 2 threes are 3 ones are 3 threes are. It will be 3, which is same as LHS. That proves P1 is true. In step 2, we will assume that Pk is true. So from this Pn, we write 1 into 3 plus 2 into 5 plus 3 into 7 plus so on and so forth, putting k in place of n plus k times k plus 1 equals k by 6 k plus 1 into 4k plus 5 is true. We name this 1. In step 3, we have to prove that pk plus 1 is true. So here in LHS, 1 into 3 plus 2 into 5 plus 3 into 7 plus so on and so forth. Now when this 1 is k, this 3 will be 2k plus 1. Similarly, when this 2 is k plus 1, this 5 will be 2k plus 3. Now this part, which is same as this part, is assumed to be true. So therefore for this part we will write this part. So LHS will be k by 6 into k plus 1 into 4k plus 5 plus, now we will write this part, which is k plus 1 into 2k plus 3. Now here we will take this k plus 1 common and write k plus 1 into this k by 6 into 4k plus 5, which is this part, plus 2k plus 3, which is this. It will be k plus 1 multiplied by k multiplied by 4k plus 5 will be 4k square plus 5k plus 6 multiplied by 2, 12k plus 6 multiplied by 3, 18 upon this LCM 6. It will be k plus 1 upon 6 multiplied by 4k square plus 17k plus 18, which will be k plus 1 upon 6. This part can be factorized as k plus 2 into 4k plus 9. In RHS, if I put k plus 1 in place of k, it will be k plus 1 by 6 into k plus 1 plus 1 k plus 2 into k plus 1 here, that will be 4k plus 4 ones are 4, 4 plus 5, 9, which is same as this LHS here. So therefore RHS is equal to LHS. That proves Pk plus 1 is true. Therefore, by principle of mathematical induction, we say that Pn is true for all natural numbers n. For all n greater than or equal to 1, prove that 1 square plus 2 square plus 3 square plus so on and so forth plus n square equals n into n plus 1 into 2n plus 1 upon 6. We have to prove this by the principle of mathematical induction. We will assume this statement to be Pn. In step 1, we will prove that P1 is true. So here LHS will be n square, that will be 1 square equals 1. RHS will be 1 into 1 plus 1 2 into 2n plus 1, that is 3 upon 6. 6 cancels with this 6, that is 1, which is LHS, and that proves P1 is true. In step 2, we assume that Pk is true where k is greater than or equal to 1, so is true. So therefore 1 square plus 2 square plus k square equals k into k plus 1 into 2k plus 1 upon 6 is true. We name this 1. Now in step 3, we have to prove that pk plus 1 is true. So first we will solve left hand side. 1 square plus 2 square plus 3 square plus so on and so forth plus k square plus it will be up to this. Next we have to put in place of this k plus 1 whole square. Now we know that up to this, that is according to this, we have this value which we write here, k into k plus 1 into 2k plus 1 upon 6 plus this part k plus 1 whole square. That will be k into k plus 1 into 2k plus 1 plus this 6 multiplied by k plus 1 whole square, 6 into k plus 1 whole square upon 6. We will take this k plus 1 common and write k plus 1 multiplied by k multiplied by 2k plus 1 will be 2k square plus k plus 6 multiplied by k plus 1, 6k plus 6 upon 6. That will be k plus 1 upon 6 multiplied by 2k square plus 7k plus 6. This will be k plus 1 upon 6, and this can be factorized as k plus 2 into 2k plus 3. Now in this RHS we will put k plus 1 in place of k here and write RHS equals k plus 1. This will be k plus 1 plus 1 k plus 2, and here 2 multiplied by k plus 1 will be 2k plus 3 upon 6. Now this is same as this LHS here, hence RHS equals LHS. That proves Pk plus 1 is true. So by principle of mathematical induction, we conclude that Pn is true for n greater than or equal to 1. By principle of mathematical induction, prove that summation ax raised to r minus 1, r runs from 1 to n, equals a times 1 minus x raised to n upon 1 minus x for all natural number n and for x not equal to 1. We will assume this statement to be Pn. In step 1, we will prove that P1 is true. So LHS will be a into x raised to 1 minus 1, 0, that will be a, and RHS will be a times 1 minus x raised to 1 upon 1 minus x. This 1 minus x cancels with this 1 minus x, leaving us a, which is nothing but this LHS a, and that proves P1 is true. In step 2, we assume that Pk is true for k is any other natural number. So Pk will be summation ax raised to r minus 1, r runs from 1 to k, that will be a plus ax square plus so on and so forth plus ax raised to k minus 1, that equals the right hand side a into 1 minus x raised to k upon 1 minus x. This is true and we name this 1. In step 3, we will prove that pk plus 1 is true. So for that, we write LHS equals this LHS a plus ax square plus so on and so forth plus a x raised to k minus 1 and plus ax. Now we will put k plus 1 in place of this k, so that will be k plus 1 minus 1, that is ax raised to k. Now this much part is same as this part whose value is this. So we write LHS equals a times 1 minus x raised to k upon 1 minus x plus this a x raised to k. We will take this a common from these two terms and write a multiplied by 1 minus x raised to k plus x raised to k multiplied by 1 minus x upon 1 minus x. That will be a multiplied by 1 minus x raised to k plus x raised to k minus x raised to k plus 1 upon 1 minus x raised to k plus x raised to k will be 0, and that equals a multiplied by 1 minus x raised to k plus 1 upon 1 minus x. Now in this RHS, if we put k plus 1 in place of this k, we will get RHS equals a multiplied by 1 minus x raised to k plus 1 upon 1 minus x, which is same as this left hand side. Therefore this RHS will be equal to LHS, and that proves p k plus 1 is true. So we conclude by principle of mathematical induction, Pn is true subject to these two conditions. By the principle of mathematical induction, we have to prove that 5 raised to 2n minus 1 is divisible by 6 for any natural number n. Now 5 raised to 2n minus 1 is divisible by 6 means 5 raised to 2n minus 1 is multiple of 6, which means is equal to 6m, where m is some natural number n. Now we will assume this statement to be Pn. Now in step 1 we will prove P1 is true. So left hand side will be 5 raised to 2 minus 1, 25 minus 1, 24, which can be written as 6 multiplied by 4, where 4 is a natural number. In step 2 we assume that Pk is true, where k is some natural number. So we assume Pk, which is 5 raised to 2k minus 1, 6a, where a is some natural number n. We name this 1. In step 3 we have to prove Pk plus 1 is true. So here left hand side will be 5 raised to 2 into k plus 1 minus 1, that will be equals 6b, where b is some natural number. And now that will be 5 raised to 2k into 5 square 25 minus 1. From statement 1 we get 5 raised to 2k equals 6a plus 1. Now we will substitute the value of 5 raised to 2k as 6a plus 1. So that will be 6a plus 1 multiplied by 25 minus 1, that will be 150a plus 25 minus 1, that will be 150a plus 24. We can take 6 common from this and write LHS equals 6 multiplied by 25a plus 4, which is nothing but 6b, where 25a plus 4 is some natural number b, which is same as right hand side 6b here. So that proves Pk plus 1 is true. Now by the principle of mathematical induction, we conclude that Pn is true for all natural numbers n. Prove that 2 raised to n is greater than n for all positive integers n. We will assume 2 raised to n greater than n to be the statement Pn. In step 1 we will prove P1 is true. So left hand side will be 2 raised to 1, which will be greater than the right hand side n, that is 1. So 2 greater than 1 is a true statement, which proves that P1 is true. In step 2 we assume that Pk is true for k some positive integer. Therefore, we assume 2 raised to k greater than k is true. In step 3, we will prove that pk plus 1, that is 2 raised to k plus 1 greater than k plus 1 is true. From step 2, we have 2 raised to k greater than k. We will multiply this statement by 2. That gives us 2 into 2 raised to k greater than 2k. But 2k is k plus k. That will be greater than k plus 1 according to this. So that proves 2 raised to k plus 1 is greater than k plus 1. Therefore, pk plus 1 is true. In step 4, by principle of mathematical induction, we conclude that Pn is true for all positive integers n. Friends, if you like this video, please click the like button. Share this video with your classmates. Don't forget to subscribe this channel to get more videos of this type. Give your comments to make these videos better. You can suggest topics on which you want me to make videos. See you in the next video. Until then, keep watching Number Collage. Thank you.